So last time we got maybe 2/3 the way through this group of slides. So what I'm going to do is go relatively quickly through it again and then slow down when we get to the part that we didn't cover. Okay? So basically we're talking about the lighting of arbitrary scenes as calculated. And this is kind of the 3D graphics part of things. So if you remember, there was there were things that describe the lights, and they consist of geometry, directional lights or point sources, how far are they away, whatever, and then properties, which would be the intensity of the light and the color of the light that would fall under there. And there were materials issues, which also had a geometry, and that would be, if you're talking about a facet, where is the facet in the scene? And what is the surface normal to the facet? And then there were properties, which consisted of reflectance, either for ambient illumination or for diffuse reflection or for specular reflection. So we're talking there about the shading model describes the mathematical model to use. Emphasis on the word not mathematical, emphasis on the word model. This is an approximation of reality. So we talk about illumination, lighting, shading, we saw the definitions. The models here are relatively simple. The more physically based it is, the more complicated it is to calibrate or to calculate. So light sources and materials, again, have properties, the color of the light, and they have geometrical attributes. And surface properties have geometrical attributes, that is, where they're located. They emphasize the microstructure here, but all that really does is determine the extent of diffuse illumination or diffuse reflection. Light sources can be light emitting or light reflecting. Sometimes we model a light reflecting surface as one that's actually light emitting. One good example would be moonlight, right? The moon does not emit radiation. It's reflected from the sun, but for all intents and purposes, you could pretend that the moon is emitting radiation. Okay, ambient light sources. Talking about light that does not have a geometry, it does not have a direction associated with it, does not have a position associated with it. Basically, it's light that comes from everywhere and nowhere. And my analogy is the light you see on a foggy day when you can't see the sun. That would be ambient light. Most of the light in here, well, it depends what you're looking at. But you can kind of pretend it's ambient. But if you really look carefully, I can see the reflection of the lights coming off of the table there, so that would be not a result of ambient light. Okay, so here's a scene that's calculated based solely on ambient light. You can tell what color things are, but you have no variation in shading that allows you to determine the shape, other than guessing that that's going to be a sphere and it's on a plane. So then we have directional light sources. directional lights, all come from the same direction. The sun is a good model of a directional light, at least so long as you're not actually looking at it. And when you have directional lights, now you can tell shading gives you a little bit of an idea, that's better, of the fact that the shading varies over the surface in a way that is reminiscent of a sphere, allows you to establish the shape of the object as being spherical. And we have point light sources, so we have directional light sources and point light sources. And here's ambient combined with a point light source. We can also have spotlight-like sources where the light is confined to a cone of illumination. That would be a spotlight. You can have they call it an area light source. I would call it an extended light source. One of the characteristics of extended light sources is you don't get sharp shadows because each point gives rise to a different shadow, so you get kind of a soft shadow effect. I'm talking about reflection. Light comes in, it bounces off in all directions. The reason for the diffuse reflection is because of the texture of the surface. The more rough the surface, the more diffuse the reflection is. Smoother the surface, there's still a diffuse component to it, but the more likely it is to look like a mirror-like surface. So ideal, okay, all directions. Then the ideal law for diffuse reflection is the cosine law, Lambert's cosine law, which says that the amount, it's scattered in all directions, but the amount of scattered depends on the cosine of the angle that the light is making with the surface normal. And it explicitly does not depend on where the viewer is. It only depends on the light source and the surface normal. And there's the geometry of it, so it's basically the dot product between the surface normal and the direction to the light. And here's some examples of it. Okay, most light sources, particularly point light, directional light sources, usually you don't regard those as changing with distance, but point light sources you do. And if you're far enough away that it looks like a point source, the model would be inverse square law. But in empirical models, where you're judging things by kind of the way they appear, you often include the linear and the constant term in there. Okay, that's diffuse reflection. Ambient light can be directional, or point, or extended, or spotlight. Okay, reflection, you have ambient reflection, you'll have diffuse reflection, and you have specular reflection. So shining surfaces, okay, produces an effect known as a specular highlight. That is basically where the light is bouncing off the surface and into the observer's camera or eye or whatever, and you get a little shiny spot there. That's the same color as the light source. So look, smooth, mirror surface, smoother it is, the more like a mirror. So basically what we're saying is that the maximum effect occurs where at the angle that satisfies the law of reflection. So when the observer is right in the same direction as the reflected beam, you're going to get the maximum effect. Theoretically, if you're off that angle, you don't see anything for a perfect mirror reflection, but generally specular reflection includes a little bit of scatter, a little bit of spread. So that's often modeled on that. That's the non-ideal specular reflectance. Skip ahead to this. So we're saying that the reflected or the reflected light actually goes through kind of a conical. And what you say is, it diminishes the further off the reflection. The maximum is where the law is satisfied exactly, but then it drops off from there. And at angles greater than this, you don't see the specular highlights. You have to be within that cone. Okay, that's called Phong lighting, and the math is given right here. You calculate the angle between the reflected light and the direction of the observer, goes as the cosine of that light. You also can model the width of the specular reflection. Typically it's a power law, so there's a shininess coefficient that you raise to cosine 2. The bigger that coefficient, the more sharp the specular reflectance is. This is an empirical model. It looks approximately correct. It's not an exact, there's no physics in the term. Okay. Here's how it varies with shininess. We won't worry about that. There is a formula for calculating the angle, and then angle of reflectance given the surface normal and the direction of the light. Plug that into the dot product with the viewer distance, and that gives you the cosine of the angle phi. And you can spend a little time talking about how you actually calculate that R vector. But we won't worry about that. And so here's some examples of Phong lighting. So basically, the more spread out the highlight is, the smaller that shininess coefficient is. So if you have a very high shininess coefficient, you're going to get just a single spot there. You can, if you're looking at something like at a sphere, I've said that the one argument for seeing the shininess is that you have to be in the right position. Another argument is that it's okay to be in the wrong position if you're looking at something like a sphere, because there's some point on the sphere for which it's going to satisfy the law of reflection, and that's where you're going to see the highlight. So sometimes it's not a case of not seeing the highlight, it's a case of where do you see the highlight, and that depends on the direction of the observer or viewer. So if we put everything in there, we have the lighting model consists of our three terms. There's the ambient illumination term, there's the diffuse illumination term, there's the diffuse reflectance term, and the specular reflectance term. And the latter two have to be summed over the number of light sources in the scene. So it can be a significant amount of calculation. We also emphasize that all of these reflectances and the illumination depend on color. So the way that's handled is you do the calculation in red, you do the calculation in green, you do the calculation in blue, and then you look at the RGB value of the final result. And we saw this. This is kind of showing the mixture of the specular component and the diffuse component. So there's the angle of incidence. The closer you are to normal incidence, the greater the diffuse reflectance. And here is the specular component. And here doesn't matter, right? What the angle of illumination is. All that determines is the direction of reflectance. So this shape is the same as you go up. Right? So if you combine the two, you can kind of see the combined pattern of the reflectance, except I don't really like that because it doesn't talk about the fact that the wavelengths are totally different, the colors are different. That makes you think that it's the same, just combined to a higher, more complicated geometric shape. So I don't like the third total. Okay. This is where we ended up, near as I can remember. This was the last slide we showed last time. All right, so we're on to new material. And the new material says, okay, we have all of these formulas. How do we actually perform them? All right? So this general topic is called the shading model. Okay, so this talks about how you do it. And there's 3 different shading models, kind of in order from the simplest to enact to the most complicated to enact. By complicated, we mean the amount of equations that you have to calculate, right? However, the more complicated ones are more realistic or more believable than the not complicated ones. All right. So the first of the models, well, before we talk about that, go to this slide. So basically, we are looking, almost always, we're looking at polygonal models. So we have little facets, and hopefully they're little facets because that gives you, better sampling of the area and more realistic. But you're still dealing with those facets. Okay, so our first model is called flat shading. What flat shading does or says is that you take a polygonal facet, let's assume it's a triangle, and you calculate the surface normal to that little flat facet, and then you calculate the shading for that situation, okay? And then you apply that to the entire facet, okay? That is flat shading. The same value over the entire facet, okay? And what that does is it gives you little regions of constant color, right? As you can kind of see on the Utah teapot there. However, there's a problem with that. First of all, if the facets are reasonably big, you can, no matter what the lighting is, you can identify the facets. And where that is the strongest is if you look at the edge contour. And the facets there are going to show up as sharp lines with sharp angles between them if the facets are big. As the facets get smaller and smaller, the contours are going to look smoother and smoother. Right? So that's one thing that tells you that you've got a faceted model. And you know, that's an artifact because you know it's supposed to be a smooth surface, not, I mean, a smooth surface, not a flat surface. The other thing you can tell is if you look at the facets, you can see the boundary between the facets, okay? And the fact that you can see the boundary clearly is due to a phenomena in the eye, or a phenomena due to the eye called Mach banding. Okay? So, we'll talk about Mach bands. So let's assume that we have a sharp change in illumination from one point to the next, all right? Because one facet is this color, the other facet is darker by an amount, and it changes abruptly at that point, okay? Now, how does the eye work? Well, the eye works with a chemical phenomenon. There's a little chemical compounds, and what they're doing is they are enabling the components of the eye to see things. So, if you have a bright area, right near the border, you're going to use the compound up adjacent to the border. So some of that chemistry, some of those materials are going to migrate from here to over there. Okay? So what happens is near the edge, that actually enhances the reception because you have these, what do they call it? Having trouble with the word here. What is the chemical that enables a reaction but doesn't get used up itself? There's a name for that. Pardon? We'll know it if we think of it. Okay. My chemistry's a little rusty here. Okay, so what happens here? All right. Well, at this side, some of the compounds and materials have been used up by the neighbor, so there's not enough available here, and you get that phenomena. So when you get close to an edge with Mach banding, the bright edge looks brighter, the dark side looks darker. And that gives you an exaggerated sense of where the band is. Right? So I don't know if this slide is good enough to see it. I think I can see it. You know, the brighter side, it's a little lighter, and then the darker side, right at the edge, it's a little bit darker. All right, this is a perception thing. Let's see. Does that help? You see it now? Okay, so that's Mach banding. And that says what you really would have liked is smoothing at the edge. That would have blended things better. But Mach banding goes exactly the opposite way. Okay, so vertex